The year was 1903, when I became the first woman to receive a Nobel Prize in Physics, sharing the honor with my husband Pierre and I Becquerel for a discovery that defied everything physicists believed possible. 8 years after that, I claimed a second Nobel Prize in chemistry, which made me the only person in history to win Nobel Prizes in 2 different sciences. I mention this not out of pride, but so you understand exactly who is telling you this. When I say radioactive decay breaks every intuition you have about matter, those words carry the weight of someone who measured the impossible and forced an entire scientific establishment to accept it. What should have been impossible was this: a piece of uranium sitting in complete darkness, producing energy from nothing at all. Day after day, the energy came. Year after year, it continued, with no heat applied and no light shining on it, and no chemical reaction driving it forward. Nothing but a lump of metal radiating invisible rays that could pass straight through solid matter and leave their mark on photographic plates. The most accomplished physicists alive insisted this violated the sacred principle of energy conservation, that energy cannot simply appear from nowhere. Pierre and I measured it anyway, using instruments sensitive enough to detect the electrical charge from a single ray. And what we found did more than challenge physics. It revealed that every atom in the universe carries an internal clock counting down toward its own transformation. You believe you understand radioactive decay because you have heard the word countless times, and you picture atoms falling apart while releasing energy and becoming something else entirely. But here's the thing I need you to consider. If matter holds itself together with such tremendous force, if atoms maintain their structure against all odds, then what would compel any atom to destroy itself? This question consumed me during the years I spent in that leaking shed on Rue Lomond, where the Sorbonne refused to provide us with proper laboratory space despite the importance of our work. Where does the energy originate, and why does any of this happen at all? Travel back with me to 1895 and a laboratory in Würzburg, Germany, where Wilhelm Röntgen had just discovered X-rays, a form of invisible radiation capable of passing through human flesh to reveal bones on photographic plates. The discovery sent electricity through the scientific world, and physicists everywhere began hunting for similar invisible rays. Henri Becquerel worked in Paris at the time and wondered whether phosphorescent materials, the substances that glow after absorbing light, might produce rays similar to what Röntgen had found. He placed uranium salts on photographic plates wrapped in black paper, planning to expose everything to sunlight and check whether the uranium would emit penetrating rays of its own. But Paris turned cloudy and stayed that way for several days, which meant the plates sat untouched in a drawer while complete darkness surrounded them and the uranium rested on top. When Becquerel finally developed those plates, expecting to find nothing at all, what he saw instead was strong fogging across the images, as if light had somehow struck them despite the darkness. Most explanations stop right here and call this the discovery of radioactivity before moving quickly to the next topic. What they miss entirely is the genuine terror this accident created in the physics community. Decades later, Alexander Fleming would discover penicillin through equally careless luck when he neglected to clean a contaminated petri dish. But that accident merely revealed a hidden property of mold. What Becquerel stumbled upon suggested the fundamental laws of physics might be wrong, that a piece of uranium could create energy from absolutely nothing, that perpetual motion might actually exist. The physicists who learned of this were not merely curious about it, and they were not simply intrigued. They were frightened, because everything they understood about the universe insisted this could not happen. When I began my doctoral research on Becquerel's rays in 1897, I made a decision that proved to be the difference between speculation and proof. Other scientists observed these rays and described them in qualitative terms, and theorized about their nature without committing to measurements. I chose to measure them with precision, to attach numbers to what everyone else was guessing at. Pierre's piezoelectric quartz electrometer became my primary instrument, a device he and his brother Jacques had developed years earlier that could detect electrical currents so faint that no previous instrument had registered them at all. Becquerel's rays ionized the air they passed through by stripping electrons from atoms, and this created a tiny current that Pierre's electrometer could measure exactly. What I did next was work that other scientists considered tedious and beneath their dignity. I tested every element and compound I could get my hands on, systematically and repeatedly. Uranium oxide, uranium chloride, uranium dissolved in acid, uranium in crystite, uranium suspended in glass. Dozens upon dozens of compounds, each measured again and again until patterns emerged from the data. And here's where the first revelation appeared. The intensity of the radiation depended only on the quantity of uranium present in the sample, not on its chemical composition or whether the uranium bonded to oxygen or chlorine or sat entirely alone. Temperature made no difference, illumination changed nothing, and the chemical state had zero effect on the radioactivity, which meant only one thing mattered: how many uranium atoms were in the sample. This finding should strike you as deeply strange if you consider what chemistry actually studies. Chemistry is the science of how atoms combine and react, and every chemical property we know, from color to hardness to melting point to reactivity, depends on how atoms bond with other atoms. But here was a property that ignored chemistry completely, where uranium atoms radiated with equal intensity, whether bonded to 2 oxygen atoms or 4 chlorine atoms or nothing whatsoever. Insurance actuaries build entire careers on a similar insight, and they do it by predicting not when any individual person will die, but how many people from a given demographic will die within a specific year. The randomness of individuals produces the predictability of populations. And this is the mathematics of large numbers, the same mathematics that guarantees casino owners their profits over time. What I observed in those uranium compounds was this exact mathematics operating inside atoms themselves. The radiation came not from the surface of the uranium, and not from its chemical bonds, but from somewhere far deeper, from the core of the atom, from a place that chemistry could never reach. This became the first great revelation. Radioactivity is an atomic property that emerges from within the atom and has nothing to do with chemistry. It is something far more fundamental than any chemical reaction. If radioactivity ignores chemistry and temperature and every external condition we can control, then what process inside the atom produces these rays? And the question that troubled physicists more than any other: where does all that energy come from? Consider what Pierre and I actually measured. A single gram of radium, the element we isolated through 4 years of brutal physical labor that involved crushing and dissolving and filtering 8 tons of pitchblende residue entirely by hand. That tiny gram produced enough heat to melt its own weight in ice every single hour. Not once, but continuously. Hour after hour and day after day and year after year, with no external power source driving it. No chemical reaction known to science could sustain such output for any length of time. Burning coal, which was the most energetic chemical reaction anyone had studied, would exhaust itself in moments if forced to produce such concentrated power from such a small amount of material. But the radium showed no signs of exhausting itself, continuing its energy output relentlessly, with only the most gradual decline over years and decades. The energy had to originate somewhere, and there was only one place it could possibly come from: the atom itself. Think of the mathematics this way. Bankers use exponential growth to build fortunes, starting with a small amount of interest that compounds over time into enormous wealth. Radioactive atoms use the exact same exponential curve, but in reverse, spending their vast internal stores bit by bit across time scales that dwarf human experience entirely. The graph tracking a growing investment and the graph tracking radioactive decay are perfect mirror images of each other. The atom turned out not to be the simple, solid, indivisible billiard ball that many physicists still imagined in those days. It was a warehouse containing unimaginable quantities of energy, a reservoir so vast that it could radiate heat for centuries and for millennia, and still have more energy left to release. And through some process we did not yet understand, this energy was bleeding out into the universe. In 1898, while I analyzed the radioactivity of various uranium ores, a puzzle appeared in my data that made no sense at first. Pitch blende, a uranium ore that came from the mines of Bohemia, registered as more radioactive than pure uranium itself. This seemed impossible on its face, because how could removing other elements from uranium make the remaining uranium less radioactive rather than more? Only one explanation fit the evidence. The pitch blende must contain another element that nobody had ever discovered, something far more radioactive than uranium. Pierre abandoned his own research to work alongside me, and together in that shed on Rue Lormont with its dirt floor and leaking roof, we began the work of isolating this unknown element. We obtained ton after ton of pitch blende residue from the Joachimsthal mines, material the miners themselves considered worthless. And we crushed it and dissolved it in acid and filtered it and precipitated it and separated it into fractions. We measured each fraction's radioactivity and kept only the most active portions and discarded everything else, and then we repeated the entire process from the beginning. The first element we found, I named polonium after Poland, my homeland that suffered under foreign occupation at the time. But something even more radioactive remained hidden in the residue, which meant the purification had to continue. 4 years of physical labor followed, with buckets of solution carried by hand and boiling vats stirred and fumes breathed in that surely damaged our bodies. All of that work, all of that time, all of that suffering produced 1/10 of a gram of a new element extracted from 8 tons of ore. He named it radium, from the Latin word for ray. 1/10 of a gram, a quantity you could barely see with your naked eye. But that tiny speck of matter proved radium existed, and we determined its atomic weight to be 226, making it the heaviest element anyone had discovered up to that point. And we established its proper position in Dmitri Mendeleev's periodic table. Today, the unit of radioactivity, called the Becquerel, honors Henri's original discovery, while the older unit, called the Curie, represents 37 billion atomic disintegrations occurring every single second, which is the activity level of 1 gram of radium-226. When we first observed radium in darkness, the glow it produced stopped us in our tracks. A soft blue luminescence visible to the naked eye emanated from within the element itself, and I found this glow beautiful in a way I cannot fully describe. I kept tubes of radium solution on my nightstand to watch them shine through the dark hours. I carried samples in my pockets wherever I went. Pierre would demonstrate radium's glow during his lectures, holding the tubes in his bare hands for the audience to see. We did not understand what we were doing to ourselves. The radiation passing through our flesh was ionizing the molecules in our bodies, breaking chemical bonds and disrupting the delicate machinery that kept our cells functioning. My fingers developed cracks that would not heal, and painful sores appeared that persisted for months. Pierre suffered similar wounds that seemed to resist all treatment. Ernest Rutherford, working in Montreal at the time, had begun classifying these emissions into distinct categories. He named them alpha rays, beta rays, and gamma rays, using letters from the Greek alphabet. And he discovered that alpha rays were heavy and stopped easily by paper, while beta rays were lighter and more penetrating, and gamma rays passed through nearly everything we put in their path. All 3 types were damaging living tissue in ways nobody recognized at first. The young women who painted watch dials with radium paint in American factories, the workers who came to be known as the Radium Girls, pointed their brushes with their lips to create fine strokes for the delicate lettering. They glowed in the dark when they walked home at night, and their co-workers thought it was wonderful. And then they died, their jaws rotting away and their bones crumbling from radiation damage that doctors could neither diagnose nor understand until far too late. My laboratory notebooks from those years now sit in the Bibliothèque Nationale de France inside lead-lined boxes that will contain their radioactivity for another 1,500 500 years. Anyone who wishes to examine them must sign a liability waiver and wear protective equipment throughout their research. This is part of what I left behind, not just knowledge but contamination that will outlast centuries of human history. But I have not yet explained the most shocking discovery, what actually happens when an atom decays. When a radium atom emits an alpha particle, which is a cluster containing 2 protons and 2 neutrons, that atom does not remain radium and cannot possibly remain radium. It has lost part of its nucleus, which means it has become a completely different element with completely different chemical properties. Radium becomes radon, a gas that behaves nothing like the metal it came from. And radon is itself unstable, which means it decays into polonium, and polonium decays into lead, and lead transforms into bismuth. And the chain of transformations continues through element after element until finally a stable configuration is reached. For 1,000 years, alchemists had tried to transform lead into gold using every method they could imagine. They heated lead, dissolved it in acid, combined it with mercury and sulfur, and chanted incantations over bubbling crucibles while searching for the philosopher's stone. They failed every single time because they were trying to change atoms through chemistry, which only rearranges the electrons in the outer shell of an atom. Chemistry cannot touch the nucleus, where an element's identity actually resides. What Pierre and I demonstrated was that atoms change themselves from within by ejecting pieces of their own nuclei without any external intervention at all. The alchemists had pursued the right dream using entirely the wrong method. Transmutation is real, and it happens constantly, all around us. The uranium in the ground beneath your feet is slowly transforming itself into lead, atom by atom. And this process has continued since Earth formed 4.5 billion years ago, and will continue until no uranium remains. This is evolution written in matter itself. Darwin's finches adapt and transform across generations, with the least fit configurations disappearing while the better adapted persist, and atoms follow the same pattern through decay chains. The most unstable nuclear configurations vanish almost instantly while the more stable ones endure. What remains in the universe today, whether organisms or isotopes, is what has survived. They failed every single time because they were trying to change atoms through chemistry, which only rearranges the electrons in the outer shell of an atom. Chemistry cannot touch the nucleus where an element's identity actually resides. What Pierre and I demonstrated was that atoms change themselves from within by ejecting pieces of their own nuclei without any external intervention at all. The alchemists had pursued the right dream using entirely the wrong method. Transmutation is real, and it happens constantly all around us. The uranium in the ground beneath your feet is slowly transforming itself into lead, atom by atom. And this process has continued since Earth formed 4.5 billion years ago, and will continue until no uranium remains. This is evolution written in matter itself. Darwin's finches adapt and transform across generations, with the least fit configurations disappearing while the better adapted persist, and atoms follow the same pattern through decay chains. The most unstable nuclear configurations vanish almost instantly while the more stable ones endure. What remains in the universe today, whether organisms or isotopes, is what has survived. Here is something that still astonishes me despite decades of study, something that reveals the strange logic running beneath physical reality. Each individual atom has no memory of its past, no awareness of how long it has existed, no knowledge of whether neighboring atoms have already decayed. It simply exists in a state identical to every other atom of the same isotope, and at some perfectly unpredictable moment it transforms into something else entirely. But here's where it becomes strange. Gather billions of these memoryless atoms together, and they decay in perfect mathematical harmony. Exactly half of any sample of radium will have decayed after 1,600 years. Not approximately half, but exactly half. And after another 1,600 years, exactly half of what remains will have decayed as well. The fraction never changes, and the time scale never varies. This is what we call the half-life, and the precision of it should astonish anyone who thinks carefully about what it means. How does randomness produce clockwork? How do atoms with no communication and no coordination and no awareness of each other behave with such collective precision despite their individual unpredictability? The answer points towards something deep about how matter is structured at its most fundamental level. Every radium atom has exactly the same probability of decaying in the next second, and that probability is fixed by the internal structure of the nucleus itself, by the delicate balance between the electromagnetic force pushing protons apart and the nuclear force holding them together. Each atom rolls the same weighted dice every moment of its existence. When billions of atoms roll those identical dice at the same time, the aggregate outcome becomes inevitable despite the randomness of each individual roll. The unpredictability of individuals produces the precision of populations, and this same mathematics governs casino profits and insurance premiums and the behavior of radioactive matter across the universe. Statistics runs everything. Inside a single gram of radium, 37 billion atoms transform themselves every second. That number is so large it becomes difficult to grasp. 37 billion nuclear events occurring in less time than it takes your heart to beat once. Each transformation releases energy and ejects particles and creates daughter elements that will themselves decay in turn. This cascade has continued for billions of years and will continue for billions more. When I held those glowing tubes in my hands, I was witnessing atomic violence made visible without understanding what I saw. The blue light came from radiation striking the glass and exciting atoms that released photons in response. The warmth I felt came from particles ejected from nuclei at tremendous speeds, their kinetic energy converting to heat against my skin. The damage to my flesh came from those same particles tearing through tissue and ionizing molecules that had no defense against such assault. The atoms in your own body are not silent either. Carbon, 1,4, created when cosmic rays strike nitrogen in the upper atmosphere, enters every living thing through food and breath. It decays with a half-life of 5,730 years, which means that when archaeologists date ancient artifacts using radiocarbon dating, they are reading an atomic clock built into all organic matter. Your bones, your muscles, your brain all contain atoms that are slowly and quietly transforming themselves while you read these words. You are not a fixed thing, but a temporary arrangement of matter that is itself in constant flux, not a noun, but a verb. During the Great War, I saw what this knowledge could accomplish for humanity when properly applied. I equipped automobiles with X-ray machines that soldiers came to call petites Curies, and I drove those vehicles to the front lines myself. My daughter Irene, who would later win her own Nobel Prize for discovering artificial radioactivity, worked alongside me, training nurses to operate the equipment, to locate bullets lodged in wounded soldiers, to guide surgeons performing desperate operations in field hospitals. Radiation could heal when used properly, and it could also kill when misused or misunderstood. The same emissions that revealed shrapnel positions could destroy cancerous tumors, and today radiation therapy treats cancers that would otherwise be death sentences. Smoke detectors in your home contain tiny amounts of americium, 241, an element whose radiation ionizes air particles to detect smoke from fires. Nuclear medicine uses radioactive tracers to create images of living bodies, to track blood flow, to locate diseases hiding in tissues where no other imaging technique can see them. But I was never naive about what we had uncovered. I knew that understanding the energy locked inside atoms would tempt humanity toward destruction. The energy contained in matter is almost incomprehensible in scale. A single gram of any substance, if fully converted to energy through Einstein's equation, would release power equivalent to thousands of tons of explosive. Radioactive decay releases only a fraction of this energy, slowly and steadily over long periods of time. But I sensed even then that if humans learned to trigger nuclear transformations at will, the consequences would be terrible beyond imagining. The Manhattan Project, and Hiroshima and Nagasaki, Chernobyl and Fukushima, these were not my legacy directly, but they grew from the seeds that Pierre and I planted in that leaking shed. What does it mean that matter refuses to stay stable? What does it mean that atoms decay and transform and radiate energy across timescales that make human existence seem like a flash of lightning? It means the universe is not static and never was. The elements are not eternal categories fixed at the beginning of time and persisting unchanged forever after. They are stages in a process that continues without end. The heavy elements forged in ancient supernovae billions of years ago are still settling, still transforming, still releasing the energy of their violent births. The ground beneath your feet is warm because uranium and thorium decay inside Earth's mantle, producing enough heat to drive plate tectonics and volcanism across the entire planet. The continents drift on convection currents powered by radioactive decay occurring deep below the surface. The magnetic field that shields Earth from solar radiation exists because the planet's core remains molten, heated continuously from within by atomic transformations that have lasted 4.5 billion years. Everything changes, and that is the lesson radioactivity teaches. Atoms do not endure forever, and neither do stars or species or civilizations. We are all temporary arrangements of matter, patterns persisting for a moment against the relentless tendency of the universe toward transformation. But here is what I find beautiful about all of this, what moves me still after years of study. Because radioactive decay is so regular and so mathematically precise in its aggregate behavior, we can use it to measure time itself across spans that dwarf human comprehension. The ratio of uranium to lead in a rock tells us when that rock first formed. The ratio of carbon, 1:4 to carbon 12 inches of fossil, tells us when that organism drew its last breath. Radioactive decay gave us a clock spanning billions of years, and with that clock we learned to read the deep history of our planet and our cosmos. In understanding how matter transforms, we learned to read the autobiography of the universe itself. The work was hard and the costs were real, and I paid them without fully understanding what I was paying. Pierre died in 1906, struck down by a horse-drawn carriage on a rain-slicked Paris street, and he never saw all that our work would become. I continued alone after that, becoming the first female professor at the Sorbonne, while the French Academy of Sciences continued to refuse me membership simply because I was a woman. I died in 1934 from what was almost certainly aplastic anemia caused by decades of radiation exposure, and I do not regret a single moment of the work that killed me. What we learned was worth any price. Science is not merely useful, not merely practical, not merely a way to build better machines or treat more diseases. Understanding nature represents a human achievement of the highest possible order. To see beneath the surface of things, to uncover the hidden processes that shape reality, to know truly and deeply how the universe works. This is what we are meant to do. Radioactive decay is not a mere curiosity of physics. It is a window into the structure of matter, into the nature of change, into the architecture of the cosmos itself. When I watched that blue glow in the darkness of our laboratory, I was seeing atoms in the act of transformation. I was witnessing the universe in the process of becoming. That is what radioactive decay truly means. Not the death of atoms, but their metamorphosis. Not destruction, but change. The universe does not stand still and never has. Even matter itself, the seemingly solid foundation of everything that exists, flows and transforms across timescales beyond human comprehension. The atoms do not endure, and neither do we. But what we learn, the knowledge we extract from nature through labor and curiosity and sacrifice, this can outlast us. This can grow and spread and build upon itself. This is our contribution to something larger than any individual life can contain. That is the meaning of what we discovered, and that, in the end, is why any of it mattered at all.